Jai Hind everyone. I am Jyoti Sharma, Assistant Professor in Electrical and Electronics Engineering, giving you a presentation lecture series on the topic transformer, which is unit 3 of the subject Basic Electrical Engineering, having the code KEE101 according to AKTU. Okay, in the previous lectures, first and second lecture, we have discussed what is the working principle of the transformer, what is the EMF equation, why do we call transformer as a constant frequency device. Then we have seen what are the characteristics of an ideal transformer, how does the transformer behaves when it is being working on a no load condition. Then a transformer working on loaded condition, and why we used to say that with the variation in the load, the transformer flux is always remaining constant. We have seen that in the previous lecture. Now, in the lecture 3, today's contents would be equivalent resistance, reactance and impedance of the transformer, right. Then what is the equivalent circuit of the transformer for going for various analysis purpose, likewise for finding the efficiency of the transformer, for finding voltage regulation of the transformer, we need to have the equivalent circuit of it. Then also we need to have the complete phasor diagram of the practical transformer working on loaded condition. Now, what are the losses in the transformers and thereby going to the efficiency. Now, coming to the equivalent resistance of the transformer. Now, the primary and the secondary winding of an actual transformer have some resistance which is represented by say R1 and R2 respectively. The resistances of the two windings can be transferred to any one side, and it is done in order to make the calculations easy. So, the resistance is transferred from one side to the other side in such a manner that the percentage voltage drop that remains the same on the either side, right. So, the equivalent resistance of the transformer according to formula, if it I say R1, that is the primary winding resistance, and R2 is the secondary winding resistance. In that case, and also K, that is being given as a transformation ratio given by N2 by N1, V2 by V1, E2 by E1, or in terms of current I1 by I2, then the secondary resistance referred to the primary, right, because the primary resistance is going to remain the same, right, but the secondary resistance we are going to refer it towards the primary side, its value is now changed to R2 dash and can be calculated as R2 dash is given by R2 by K square. Similarly, the equivalent resistance of the transformer referred to the primary is represented by that total equivalent resistance. If we just see, the primary resistance is as it is, the secondary resistance which is R2, after referring towards the primary side, the value of it becomes R2 dash is equals to R2 by K square. And that complete equivalent resistance of the transformer referred to primary, this is R01, that will be given by R1 plus R2 dash, where R2 dash is given by R2 by K square. Moving on to the equivalent resistance of the transformer referred to now secondary, right. The complete resistance of the transformer now it can be referred to secondary side. So, if you just see the primary resistance referred to the secondary is now denoted by R1 dash, R2 is as it is, right, and the R1, the primary resistance, that needs to be referred towards the secondary side, its value would be changed given by R1 dash, right. So, here you can see R2 is as it is, R1 needs to be transformed towards the secondary side. While doing that, if you just see, its value will become R1 dash, that is K square of R1 times. So that the total equivalent resistance of the transformer when referred to secondary, that value becomes R1 dash plus R2, where the value of this R1 dash is K square R1, right. Similarly, we used to have, this is all about the equivalent resistance of the transformer, we also used to have an equivalent leakage reactance of the transformer, right. What is this leakage reactance? So, if you just see, the flux that links with both the windings of the transformer is called the mutual flux, and the flux which links only with one winding of the transformer is called leakage flux. It doesn't reach up to the another winding, right? Due to the leakage flux of the primary winding and the secondary winding, an EMF is induced in the respective windings. The primary and the secondary voltages will have to overcome these induced EMFs. Thus, these induced EMFs are considered as the voltage drops across the fictitious reactance placed in the series with the primary and the secondary winding. These reactances are being called as leakage reactance. As we have done in case of resistances, the reactances can also be transferred to either of the side, either towards the primary or referred towards the secondary, right. So, if you just see the equivalent reactance of the transformer referred to primary. So, if at all I just say that X1 is nothing but the primary winding reactance, it is actually the primary winding leakage reactance. Similarly, X2, that is secondary winding leakage reactance with the K as the transformation ratio, then the secondary leakage reactance to the primary X2 dash can be calculated by the formula. Once again, as we have done in case of resistance, there it was R2 dash given by R2 by K square. Similarly, here also I can be having X2 dash is equals to X2 by K square. So that the equivalent reactance of the transformer referred towards the primary, which we call it as X01, that will be given by X1 is as it is, we are not changing that, we are referring the complete reactance towards primary. Primary reactance is as it is, the secondary reactance needs to be transformed with that X2 dash. So, it is X1 plus X2 dash, where the value of X2 dash is X2 by K square, right. Similarly, the equivalent reactance of the transformer referred towards secondary, this time the secondary reactance is as it is, the X2 is remaining as it is. Now, what we are doing? We are transforming this X1 primary leakage reactance towards secondary side. So, that value will become X1 dash, which is given by K square of X1. So, the total equivalent reactance of the transformer referred towards secondary given by X02, that will be equal to X2 plus X1 dash. And what is X1 dash? X1 dash is K square X1, right. Likewise, till now we have seen that we can refer the resistances and we can refer the reactances towards the primary and secondary. Combiningly, I can give the equivalent impedance of the transformer either referred towards primary side or referred towards the secondary side, right. So, the primary impedance, if at all, so Z1 would be given by R1 plus JX1. Similarly, secondary impedance would be given by R2 plus JX2. So, the transfer of the impedances takes place on the same line as that of the resistances. So, the transfer of the impedances can take place from primary to secondary and from secondary to primary. So, if at all I just say that Z01, that is Z01, that is the equivalent impedance of the transformer referred towards primary. 1 denotes primary and 2 denotes secondary. So, it is equivalent impedance of the transformer referred towards primary, that will be given by R0 square plus R0 X0 square under root, right. Similarly, the equivalent impedance of the transformer referred towards secondary, that will be given by under root of R0 square plus X0 2 whole square, under root of that, right. So, this is equivalent impedance referred towards primary and this is the equivalent impedance referred towards secondary. Now, coming to we have till now seen what will be the equivalent resistance referred towards primary, towards secondary, reactances towards primary and secondary, impedances referred towards primary and secondary. But while going for the analysis of the transformer, for calculation purposes, for finding efficiency, for drawing the phasor diagram of the transformer, for finding voltage regulation of the transformer, we need to have the equivalent circuit of the transformer, which gives us the picture of the transformer and its working, right. So, going for the exact equivalent circuit of the transformer where no value is being referred toward any one of the side, right? No referring is now taking place. It is the exact equivalent circuit of the transformer. So, if we just see in this is the equivalent circuit of the transformer. The notation by which we give the transformer is with the two windings, primary and secondary, with the mutual coupling being shown by the two lines, vertical lines. Then on the primary side, we will be having the input voltage being given as V1, right? R1 denotes the primary winding resistance. X1 denotes the primary leakage reactance, right? I1, what is I1? I1 is the rated primary current of the transformer. We know that this I1 rated primary current of the transformer is actually the phasor sum of I0 and I2 dash, right? So, I need to have this I1 being split into two. One is I0. What is I0? It is the no load current, primary current, and I2 dash, it is that load current which is being taken by the transformer when the transformer is being loaded because of the loading effect, right? So, it has been divided. Now, once again going for the no load circuit, this is the no load circuit being shown. So, for the no load circuit, if at all we see, once again I know that my no load current is once again the phasor sum of the two components. What are the two components? One is the magnetizing current and another one is the working component, right? We actually also used to call it as I mu. So, once again the working current and the magnetizing current. But these are the currents which are flowing in the transformer when I am drawing the equivalent circuit of it. Now, these currents are flowing in certain elements, right? This is the working component, right, giving me the losses. Which losses? The core losses. We have discussed that because it will be having a very much negligible amount of copper losses. So, this is the working component. So, I need to show it with the resistance, a fictitious resistance. That resistance I am calling it as R0, okay. Then this is the magnetizing current, right? Magnetizing current which is responsible for the production of the flux in the core, and this is exactly happening with the inductive winding. So, I need to show it with inductance, a fictitious reactance which we call it as X0, right. So, these are the specifications. So, we have seen the primary current would be divided into no load current and I2 dash. The no load circuit that comprises of the working component, the magnetizing component, working component flowing in the fictitious resistance R0, magnetizing current flowing in the fictitious reactance X0. Coming to I2 dash, we know that this I2 dash is what? It is some minus k times of I2. Yes? Then this I2 dash must be flowing in the primary winding of the transformer, thereby giving us the primary induced EMF which we denoted as E1. So, the primary circuit is now completed. Coming to the secondary circuit. Now, once again we know that when the same flux links with the secondary, I will be having an EMF produced in the secondary, the RMS value of which I used to call it as E2. The load is being connected to the secondary, so I will be having a current flowing in the secondary which I used to call it as I2, right. The voltage, the terminal voltage across the load I am calling it as V2. Now, the secondary winding resistance that needs to be represented by V2, the secondary leakage reactance needs to be represented by X2. So, this complete, it gives me the exact equivalent circuit of the transformer, right, without referring any of the values. The values are not being referred anywhere, right. So, this is what we have just discussed. The value for this R0, what we just discussed in case of the circuit, the value of R0 that can be very easily given, right. We just discussed that the no load components would be Im and Iw, that is the magnetizing component. Just to revise, these magnetizing component according to I0, that is nothing but I0 sin phi naught, right, and the working component is the cos component, right. So, the magnetizing component Im is assumed to be flowing through a reactance which is known as the magnetizing reactance. If at all I give the value for R0, so I know that the voltage across R0 is V1. So, the value of R0 that can be very much easily calculated by V1 upon IW. Similarly, X naught, the value of X naught can be easily calculated by just giving V1 by IM, right. Now, coming to the equivalent circuit of the transformer referred to primary. Right. Now, what we are going to do? We are going to have the equivalent circuit of the transformer where all the parameters are being referred towards primary side. Okay. So, there in this particular case, we will not be showing any mutual coupling. It is understood, right, that I have referred, or we have referred the complete parameters which was there in secondary towards the primary side. So, the primary circuit will be untouched. It can be seen. The primary circuit, if you just see, that is untouched. Right. This will be remaining as it is. There is no change. The input voltage V1, the input current I1, the primary resistance R1, reactance X1, the no load circuit as it is, I2 dash as it is. Now, it can be seen that E1, which was nothing but the primary induced EMF, that is given by E1, right. Now, here it starts the secondary parameters. Now, the secondary parameters are being referred towards primary. So, we know that when the secondary resistance is being referred towards the primary side, what should be the value? The resistance will become, the resistance on the secondary side was R2, the resistance will become R2 dash and its value would be R2 by K square. Similarly, the reactance X2 dash, that will become X2 by K square. Right, or I also know that Z2, which is given by R2 plus JX2, that will become the new Z2 dash, which will be equal to R2 dash plus JX2 dash, which we just write it as Z2 dash. Similarly, the load impedance, that is ZL, right, that needs to be now transformed towards the primary side. You know that while referring all the circuit constants, likewise resistance, reactance, impedances, those would be divided by K square. So, here also it will be ZL by K square, right. Now, what about E2? The secondary induced EMF. The secondary induced EMF is E2 dash, it will be changed to E2 dash, and obviously its value would be equals to E1. And according to E2, what should be its value? It should be, if you just see our transformation ratio, E2 by E1, that is equals to K, right. So, what is my E1? E1 is E2 by K. So, what should be the E2 dash value? It should be E2 by K, right. Similarly, V2 dash, what should be the value of V2 dash in this case? Now, the value of V2 dash, that means the terminal voltage, this time its value has to be, once again the voltages are divided by K, right. So, just to remember it logically, if you just see, while transforming the circuit towards primary side, it can be seen that all the circuit constants like resistance, reactance and the impedances, that needs to be, that means the secondary parameters, the secondary circuit constants which you are referring towards the primary side, those needs to be divided by K square. The current, that has to be multiplied with K, and the voltages needs to be divided by K. This was E2 by K, V2 by K, right. So, this is the equivalent circuit of the transformer referred towards the primary. Now, equivalent circuit of the transformer referred towards secondary side. Now, when it is being referred towards secondary side, now what has to be done? Now, the secondary parameters are remaining as it is, right. So, there is no change in the secondary parameter, right. Secondary resistance R2, winding resistance, secondary reactance X2 as it is, then load as it is, I may even call it as ZL, the terminal voltage V2 as it is, secondary current I2 as it is, no change. The secondary induced EMF E2 also, that is also remaining same. So, what we are doing? What we are doing to this time is we are referring the complete primary circuit towards secondary. So, the complete primary circuit has to be referred, right. We are starting with the circuit constants, we know because we have already derived it. So R1 when transferred towards the secondary side, you know its value would be changed to R1 dash, and that will be equal to K square R1, right. Similarly, the reactance X1, that will become X1 dash, and its value would be K square X1. The same thing would be happening to R0. R0 will become R0 dash, that means K square R0. X0 dash, that will become K square X0. What will be happening to the currents? What will be happening to the currents? You can see, I can be having the currents being given as I1 would be changed to I1 dash. We have seen in case of the earlier one, when the currents were being transferred towards the primary side, it was being multiplied with K. Here it will be just opposite, right. So this time it will be I1 by K. The currents would be divided by the transformation ratio. The same thing happens over here for IW and IM. For IW and IM, if at all, once again IW would be changed to IW dash, right, and the value of IW dash would be given by IW by K. Similarly, IM dash, that will be equal to IM by K. I1 dash, we have just discussed I1 by K. So all the currents which we are transforming, those would be, or we are referring, those would be divided by K. What about voltages? Now this time the voltages needs to be multiplied with K. Which voltage we are transforming? Secondary voltage is as it is, V2 is as it is, V2 is as it is, E2 is as it is. We are transforming V1, making it as V1 dash. So this time it will be equals to K times of V1. Yes, and similarly E2, which is equal to E1 dash, the transformed value over here, and that will be equal to K times of E1. These can be very well related with the transformation ratio we have just derived in case of the primary. So we have seen the equivalent circuit of the transformer referred to primary, referred to secondary. Now the fifth one, or I must say the fourth one, that is the approximate equivalent circuit of the transformer. Now what we are doing in this, till now we have seen the exact equivalent circuit of the transformer referred to primary, referred to secondary. Now this is approximate equivalent circuit of the transformer referred to primary. No big change, but we can see that while referring towards primary side, you know, when we have just seen the equivalent circuit of the transformer referred to primary, this no load circuit was over here, right. Because of that, what was happening is, I wasn't able to combine these R1 and R2 dash to have me the equivalent resistance of the transformer, right. To have the equivalent resistance of the transformer R01, we know that is being given by R1 plus R2 dash, and these can be added when these two are on the same side, right, if the same current is flowing. Although we know that this I1 is almost equal to I2 dash, because this I0 is very small, very negligible amount, but although it's there, right. So what we are doing in approximate equivalent circuit is, we are shifting this no load circuit from here towards the input side, so that now this R1 and R2 dash can be combined to give me R01. Similarly, this X1 plus X2 dash can be combined to give me X0 dash, and combiningly they can be giving me equivalent impedance of the transformer referred towards primary. Then only my calculations are going to get simpler. That means deliberately, by approximating what we are doing, we are deliberately introducing a small error, right. In that, we are just shifting this no load circuit towards the supply side prior to the resistance and reactance. The same thing can be done if at all I just say it is the approximate equivalent circuit of the transformer referred to primary. I may have the approximate equivalent circuit referred to secondary. In that case, once again, the no load circuit what I was having, I may be switching, or I will be shifting that no load circuit earlier towards the R1 dash and X1 dash. If you just see here, This is the equivalent circuit of the transformer referred towards secondary. In this case, once again, if at all I deliberately make an error and I shift this no load circuit towards this side, in this case again I can combine this R1 dash and R2, this R1 dash and R2. Similarly, I can combine this X1 dash and X2 so that I can have the equivalent resistance referred to secondary, equivalent reactance referred to secondary, and thereby equivalent impedance referred to secondary, right. So, based upon what we have done till now, likewise equivalent resistance, reactance and impedance of the transformer, a numerical is there, just going for it. A 30 kVA 2400 by 120 volt 50 hertz transformer has high voltage winding resistance of 0.1 ohms and leakage reactance of 0.22 ohms. The low voltage winding reactance is 0.035 ohms and leakage reactance is 0.012 ohms. Calculate the equivalent resistance as referred to primary and secondary, equivalent resistance as referred to primary and secondary, equivalent impedance as referred to primary and secondary. We need to also find the copper losses at full load and at 75% of the full load. Okay. So, let us see what are the things being given to us. So, I am having the primary resistance, winding resistance being given to me, that is R1 that is given by 0.1 ohms, X1 that is 0.22 ohms, R2 0.035 ohms, X2 0.012 ohms, right. Now, equivalent resistance referred to primary, we know that. So, R1E, or which we call it as R01, that is being given by R1 plus R1 dash, right. What is this R1 dash? R2 dash, this is R1.1, R2 dash, that is being given by K square R2, right. What is the value for the R2? 0.035, that is there. And what about K? How can I give K? K is nothing but 2400 by 120 whole square, right. In fact this is 0.035 upon K square, right, or I may, and what is the K being given over here? In that case, K is being given as 120 by 2400, right. So, I may even write it as 2400 upon 120, multiplying it and making a square of it, right. So, that will give me 14.1 ohms. Similarly, equivalent reactance referred to the primary, that will be given by R1 plus X1 would be given X1 plus X2 dash. So, X1 is already there, X2 dash is once again given by X2 by K square, right, or if at all I am making an inverse of the K, in that case I will be multiplying it. So, it is 5.02 ohms. Z1, so that can be given by under root of R1 square plus X1 square, what we just find it off, right. So, that is 0.2417 ohms, and Z2, that will be given as 0.037 ohms. Equivalent impedance referred to primary, that can be given as Z1 plus Z2 dash. What is Z1? So, Z1 we just find it off as 0.2417 plus Z2 dash, that can be given as K square of that is Z2. So, that will be 15.0515 ohms, right. Equivalent reactance referred to secondary, if we just find out X2E, that will be given by X2 plus X1 dash, that will be 0.01255 ohms. Equivalent resistance referred to secondary, in that case that will be given by R2E, R2 plus R1 dash, right. So, R2 as it is, R1 dash, that is K square R1, right. So, that's its value would be given by 0.03525 ohms. Last one, that is equivalent impedance referred to secondary, Z2E, that will be given by Z2 plus Z1 dash, right, and its value would be equal to 0.0374 ohms. What is being asked at the last is, what will be the copper losses at full load and at 75% of the full load, right. To have the copper losses, we know that the formulations can be given for the total copper losses, say at full load, that can be given by I1 square R1 plus I2 square R2. these are the copper losses which are occurring in the primary, these are the copper losses which are occurring in the secondary. So, the total copper losses can be given this way, or I may be giving the copper losses in terms of according to the primary, the equivalent circuit of the transformer referred towards primary. In that case, the current used to be flowing is just I1 square and the resistance used to be R1E or R01, the notations can change. So, this is the primary current and this is the equivalent resistance of the transformer referred toward primary, or I may even give it towards secondary side. That can be given as I2 square R2E or R01, the notations. This is the secondary current which is flowing in the transformer, and this is the equivalent resistance of the transformer referred towards secondary, right. So, if at all I just go with the very basic principle, that is the very basic formula, that is I1 square R1 plus I2 square R2. So, I1, for finding I1, it is not given, but I1 can be very easily known from the VA rating of the transformer. What is the VA rating of the transformer? If you just see, it is 30 kVA, 30 kVA 2400 by 120 volts, right. So, obviously, the primary current can be given by 30 kVA, 30 into 10 to the power of 3 divided by 2400, that will give me the primary current, that is 12.5. Similarly, the secondary rated current or the full load current, that can be given by the VA rating, that is 30 kVA divided by the secondary voltage, that is 120, so that becomes 250, right. Just substituting the value of this I1 and I2 over here and the resistances, I will be having the copper losses at full load would be given by 2.20 kilowatt. Okay, these are the full load copper losses. So, what will be the copper losses at 75% of the full load or 3/4 of the full load? We know that the copper losses, as can be seen, it varies according to the square of the load or square of the current, right. So, if the load has been reduced to 75%, in that case, what is going to happen with the losses? So, in that case, the losses will also vary according to the square of the load, right. So, if this X is, if the load has been changed to 0.75, then in that case, the losses would be 0.75 square multiplied by the full load losses, that is 2.203 kilowatt, which gives me 1.239 kilowatts. So, these would be the copper losses at 75% of the full load. Now, coming to a very important topic, that is the phasor diagram of the practical transformer. Now, when we come to the phasor diagram of the practical transformer, we need to know, because this is the complete phasor diagram, right, in which the loading conditions has to be incorporated. So, if the loading conditions has to be incorporated, then it becomes very much significant that whether the load is resistive or whether it is inductive or whether it is capacitive, right, the kind of load. Okay. So, just starting with the resistive load having a unity power factor. How to draw the complete phasor diagram of a transformer, right. So, once again, we have drawn many of the phasor diagrams. We know that the transformer phasor diagram will start with the quantity which is common to both the primary and secondary winding. Okay, what's that? That's the flux. So, we are going to start with flux. That is my reference phasor, right. Then I know that the no load current, right, the no load current, I can place it arbitrarily, although I know that it is the phasor sum of the two currents, right. One is the magnetizing current, which used to be in phase with the flux, and one is the working component which used to be in phase with the E1 or V1, right. Nevertheless, I may or may not include this right now, right. So, I may just arbitrarily place my I0, okay. So, that is the no load current flowing in the transformer. I have placed it in the very first quadrant, right. Okay. So, this is now I0. Now, what do I want, right? I want V1. Now, the transformer, it is a practical transformer. I can't say now that earlier, if the transformer is not being loaded, right, and it is an idle transformer, in that case, what we used to say is that V1 is equals to minus of E1, isn't it? Or I must say E1 is equals to minus of E1, right. Why do we used to say that? Why? Because E1 used to be the induced EMF which opposes the cause producing it, right? So we used to just show it just in opposition with the E1, right? We used to just show it in opposition. But this time, this is a practical transformer. I can't say that V1 and E1 would be just exactly equal, right? Why? Because now this V1 has to overcome the drops. Which drops? So the equation for V1 this time becomes, it becomes V1 is equals to minus of E1 plus I1 R1 plus I1 X1, right? We just mentioned it in this. V1 is equals to minus of E1 plus I1 Z1, where elaborating Z1 I am having I1 R1 and I1 X1, right? You know what is I1 and R1. R1 is the primary resistance and this is the leakage reactance. Okay, so we need to just draw, we need to have this V1, right? For doing that, I require minus of E1 first. Okay, so we'll be just plotting. I know that E1 has to be in just 90-degree lagging with the flux, right? So E1 will be just showing that 90-degree lagging with the flux. Just in opposition to that, I'll be showing minus of E1, but this is not equals to V1. Okay, this is minus of E1. Now, what I need to know? Now, I need to add, now I got this, minus of E1 I got it. Now, what I need to do? I need to add these two drops in it, I1 R1 and I1 X1. What is this? This is I1 R1. This is a resistive voltage drop which is occurring in R1 corresponding to the current I1. So, what will happen? This voltage, I1 R1 voltage, this should be in the same phase as that of I1, isn't it? So, for that I must know the phase of I1 first. What is the phase of I1? For that I need to plot I1, right? Okay, I need to plot the I1. I know that for plotting I1, it is the phasor sum of I2 dash and I0. Okay, I0 I am already having, right? I have already plotted it. I need to have I2 dash. Once again, I2 dash is nothing but minus of I2, right? For that, now I need to plot this I2. And for plotting I2, what is required? The nature of the load is required. What is the nature of the load? That is purely resistive. It means if the load is purely resistive, then the voltage across the load, what is the voltage across the load? V2, and the current flowing in the load, that is I2. These two should be in same phase, right? So, with this even over here, I arbitrarily plot my V2 over here, right? And the load, as it is purely resistive, it has to be in the same phase as that of the voltage, right? So, we have plotted V2 and I2 in the same phase, right? After that, now my I2 is being plotted. Now, I know that this I2 dash is the anti of I2. So, where I need to plot my I2 dash? I2 dash would be just opposite to this I2. So, I will be having this as I2 dash. Okay. Now, I got I0, I got I2 dash, so that the resultant current, I1 would be the resultant of I0 and this. So, I got the primary current I1. Now, what is else? Now, I got the phase of I1, where now I know where the I1 is placed. Now, what I need to do? I need to plot this I1 R1 voltage so that it is in same phase as that of I1, and it needs to be added to minus of E1, right? So, I will just draw a line which is just in parallel with I1 and needs to be added with V minus of E1 over here. This is in parallel with I1, right? And this phasor would be called as I1 R1. Now, once again, another phasor needs to be added. What is that? I1 X1. What is this? This is the reactive voltage I into X. This is a reactive voltage which needs to be added to I1 R1 in such a way that inductive voltage, that means the voltage should lead the current by 90 degree, or current should lag the voltage by 90 degree. So, I will make this voltage I1 X1 just leading this by 90 degree. And now this total phasor, what is this total phasor? This is nothing but V1. Now it can be very easily said that V1 is equals to, what is this? Minus of E1 plus I1 R1 plus I1 X1, that will give me V1. So this is the primary circuit being completed. Same way I can even have the secondary circuit being done. Now for the secondary circuit, what is the relationship between E2 and V2? Now once again, the relationship for E2 and V2 is E2 must be equals to V2 plus I2 Z2, or elaborating it, I may be writing that E2 is equals to V2 plus I2 R2 plus I2 X2. Once again the same logics has to be applied. I already know where my V2 is placed. I have already placed it. Now to it I need to add a phasor named I2 R2, which is a voltage. This is a purely resistive voltage, needs to be added in such a way that it is in same phase as that of I2. So what I need to do? I need to just make it, I need to have a phasor which is just in phase with I2 R2. So I'll just make the line a bit lengthier in the same phase. This is I2 R2. Now the another phasor, that is I2 X2, that is exactly, once again, this is an inductive voltage, needs to, in this case now the voltage should lead the current by 90 degree, right? So I should be making this I2 X2 in such a way that I'll be having this as my I2 X2, right? And now what is this phasor? This complete phasor. This complete phasor is E2. Now you can say that E2 is equals to V2 plus I2 R2 plus I2 X2. And what is this? The dotted line. That is I2 R2 plus I2 X2, and that is nothing but I2 into Z2. So this gives me the complete phasor diagram of the transformer when the load is purely resistive. In the next of the lectures, we will be discussing it with the capacitive load and with inductive load. Thanks for today. Thank you all.